So today's a special day because today is when the ChemOly students are going to be taking the Chemistry Olympiad. So good luck to all of you. Here's a quick tidbit I learned from my physics teacher. There's a state where electrons are pseudo-stable, where electrons are excited, but they're at this pseudo-stable state, which is called the metastable state, where they're pretty much stable, but they can still lose energy to get to the ground state. I don't know if that'll help. That's just something random I learned. My dog is making a racket. I'm gonna cry. Alright, anyways, today what we're gonna do is we're gonna learn about work. So, what is work in relationship to physics? Well, here's the equation. Work is equal to force dotted with distance. So, originally I was gonna use a new marker, but this one's like almost dead, so we're back to purple, yay! So, what does that mean? Work is force dotted with distance. Well, force and distance are vectors, right? Because acceleration, I said, has direction. We could be accelerating downwards, like gravity is when gravity is pulling us. And distance or displacement also has direction, right? If I started at this point and I moved to this point, right? This is the vector that's displaying the magnitude of this vector is how much distance I traveled, and the direction is the direction in which I traveled. All right. So let's dissect what this thing called dot product means. Well, a dot product is simply a way for us to multiply two vectors and get a scalar as a result. A scalar is just a normal number. Yeah, it's just a normal number. So there is a law for dot product that we'll be using, which says that this is equal to the magnitude of f, so like the size of f. If I was saying like going 10 newtons this way, I only care about the 10 newtons part, multiplied by the magnitude of d, or magnitude of s. I'm going to use s here, because s is way more fun to use. Dotted with s. And then we have to multiply that all by the cosine of theta, where theta is the angle between them. So let's imagine that we have a box here, and we're applying a constant force, right? If we're applying a constant force, then the magnitude of this force is just going to be constant, so we can just say magnitude of force is constant, so we don't have to consider any changing force where this magnitude is changing over distance. Right. The next thing we have is our displacement. So let's say our displacement is in the same direction, and we move to this point, so that's where our new box is. Alright, so what would be our work in this case? Well, our work is just the magnitude of f times the magnitude of s times the cosine of theta. What is the angle between them if they're moving in the same direction? Well, that's 0. So, one thing we know is that when theta, right, is equal to 0, what is cosine? Cosine theta, right, is equal to 1. So this simply becomes f dotted with s. Now, what if instead our box somehow moved perpendicularly, right? Instead of moving in the same direction, we move perpendicular and move here. Here's our displacement. Well, when theta is equal to 90 degrees, what happens? Our cosine theta is equal to 0. So we get magnitude of f times magnitude of s times 0. So the whole thing is 0. We have no work done if none of the work is in the direction of displacement. None of the force is in the direction of displacement. So if I was asking, right, how much work is done by gravity if I move this pen from here to here? Well, gravity pulls downwards, and my displacement was this way. So no gravitational force is acting on this pen. So I would say in the direction of the pen, so I say the work is 0. And now, last thing to consider, what if s is in this direction? What if we moved in the opposite direction? Well, theta would be 180 degrees, right? I have to move 180 degrees to go from f to s. So when cosine is 180 degrees, when theta is 180 degrees, right? Cosine theta is equal to -1. So I have a negative work. This whole thing is negative. And that's because our force is in the opposite direction of our displacement. So we have negative to indicate that they're in opposite directions. So what we've learned, work can be positive, negative, and it's 0 if none of the force is in the same direction as s. So now we're going to consider two different types of forces. The first force we're going to consider is the gravitational, work. So work is work is measured in joules. Work is measured in joules, Right, so joules. He's playing with a microphone. I don't know what he's doing. Okay, so work is measured in joules. So let's first find the units of joules. Well, work is equal to force divided with displacement. So this is pretty much just multiplication. So I'm just going to consider it as such. Units for work is joules. And then force is in newtons times what is displacement in? That's in meters. So a joule is a newton meter. Give me a sec. Alright, so joule is a newton meter. Oh, alright, that's great. So now we know what the units are in. We can also say this is a kilogram meter squared over second squared because a newton is a kilogram meter over second squared. Alright, so now we're going to introduce a new term, and that term is called energy. So what is energy? Well, energy is simply the ability to do work. And I said we would consider two types of work. Sorry, we are going to consider two types of energy. The first type of energy we're going to consider is potential energy. So why is it called potential energy? Well, potential energy is simply based on our position. And the reason it's called potential is because it's energy for where an object is. And that object has the potential to move, to have kinetic energy or motion of energy of motion. So here we have potential. Let's say we have a box, right? And it's on the top of a slide, and this is a height h. Energy, and this is mass m. Energy is the ability to do work, right? So if this box had dropped all the way down to here, how much work would be done? Well, what would be the thing that's acting on it, the force that's acting on it? Well, the force here, right, would be equal to ma, or force would be mg, right? It's the weight of the object. That's the only thing pulling it down. And then we have how much? So we have F, and we have to multiply it by our displacement, right? So which is equal to the magnitude of F times magnitude of S times cosine theta. Well, work, our force went in this direction. Our object also moved down, right? It moved downwards. We can ignore the slide for now and just say, what if the object drops straight down? Straight down. Right? It drops straight down. Imagine it goes straight. This is not straight. Imagine it's straight, right? Then cosine is 1. So we just get force times our displacement. What is our displacement? We dropped a height h. So, and our force is mg, so mgh. This is how much work this box has the potential to do just based on its height from the ground. So, we would say that the potential energy of the box is equal to mgh. And we denote potential energy using this big U. And then it's potential gravitational energy because gravity is what's going to pull it down. Gravity is what's going to do work on it. So we denote it UG is equal to mgh. Yay! Alright, so that's great. The second one we're going to do is we're going to find kinetic energy. So what is kinetic energy? Well, kinetic energy is simply the energy of motion, and the equation of it is K, our kinetic energy kinetic, is equal to 1/2 mv squared. So now you might be asking, how did we get this? Alright, there's two ways we can find what our kinetic energy is. Alright, so let's start with the first one. The first one doesn't require any calculus at all. So we know that v squared, right? Vf squared is equal to v naught squared plus 2 a delta x, right? So then here we can say, here what we can do is we can move this onto this side, so we get v squared minus, or v prime squared minus v naught squared is equal to 2a delta x, right? And then if we divide both sides by 2, and then multiply both sides by m, we get m times v prime squared minus v naught squared divided by 2 is equal to a, or ma delta x. Does this look familiar? Well, ma is equal to force, so we can say this is F, and delta x is our displacement, so we can say this is S. So this is F times S, right? F times S, that's our work. Our work is force times displacement, assuming that our force and displacement are in the same direction. So then what do we get from there? Well, we have work. This work is equal to m times v prime squared minus v naught squared, right, divided by 2. Our work is equal to this. Now, with energy of motion, we consider how much energy it had in its final position compared to its initial. So if we wanted to find like the kinetic energy of an object, we would want to say it has this kinetic energy because we started from an energy position of 0 and then we went to this final energy state. So in essence what we're doing is we're going to assume that it started with an initial velocity of 0 and we're going to find its final energy state. So this is equal to mv prime squared over 2, right? So 1/2 mv squared is equal to our kinetic energy. Is equal to this type of work. What is this type of work? This type of work is work that's done by the object moving. So we say the kinetic energy, right, the ability to do this work by moving is equal to this as well. Alright, so there's also a second way to derive this, and the second way to derive this is going to use a bit of calculus. After all, this is physics C. So we're going to say that we know that work, right, is equal to the integral of our force dotted with our displacement, right? Work is equal to this. So if you were trying to find work, we would just do this. If we were trying to find work based on a varying force, based on distance, this is how we would integrate it. In fact, let's just go over an example of that right now. This is equal to, let's say our force is equal to s squared, and all of our force acts in the direction of displacement, so we can just say s squared times ds. Right, so then what would be the work done? The work done would just be s cubed over 3 for whatever interval we did work on. So let's say maybe it's from 0 meters to 3 meters or something like that. And then that's how we can find how much work was done. So now that we know that, what we can do is we can find kinetic energy using this thing. So force is equal to mass times acceleration, right? Mass times acceleration dotted with our change in time, or change in displacement, which is equal to integral, we know that this is equal to dv over dt, dotted with ds. What else do we know? Well, we know that m, we can take out the m because it's a constant and it's not anything with respect to time, with respect to velocity, with respect to displacement, because m is not going to change as we move our object around. And we get dv, and then we can move this dt under the ds, so we have ds over dt. Wait, but isn't velocity equal to the change in position over change in time? Yes, it is. So we get m integral of velocity times dv. The integral here evaluates into 1/2 mv squared plus c. The c is our initial, we can just assume is 0 because we assume that we started at like 0 velocity or whatever, 0 energy. So we just get stuck with this, 1/2 mv squared is equal to our work. So what energy would do this work? Well, that would be our kinetic energy because this is the work that's done just because an object is moving based on its velocity. Alright, so that's something cool we did. We just proved that kinetic energy is 1/2 mv squared. So let's write down all the things that we've learned. We've learned that potential energy Ug is equal to mgh. We've learned kinetic energy Ek is equal to 1/2 mv squared. Alright, and we've proven both of these. And then we also know these things here. Sure, this thing is a bit hard to understand conceptually, so to end off the video, we'll go over a conceptual example to help you remember why work is F times S times cosine theta. So let's say we have a sun, right? And then we have a solar panel here, and it's facing in this direction. Which way are our sun rays coming in? Our sun rays are coming in this direction. If our sun rays are in the same direction as our solar panel, right, we absorb all the energy. So if the angle between them is 0, right, if the angle between them is 0 or 180 degrees, we absorb all of the energy. So we would say, we would take this energy, let's say this is our force and here's our displacement, we would do F times S, right, magnitude of F times magnitude of S. So I can just say a simple multiply sign. Then, multiplication sign. So then, so that means if, right, our force and our displacement are in the same direction, we get all of the force. 100%, 1 out of 1 of it. Cosine theta is 1, so we get 1 out of 1 of all of the force, all of the energy the sun provides. However, if we rotated this thing, so we had it like this, right, we're 90 degrees to it. So then, we get none of the energy. So if we are perpendicular, right, we get 0% the energy. Cosine theta is 0, so we get 0 out of 1 of all the energy that we could have gotten from the sun. So that's how work works. If they're perpendicular, if F and S are perpendicular, we get 0% of all the work. If F and S are not perpendicular, then we get 1 out of 1, or 100% of all the work that's done, all the energy from the sun. Alright, so yeah, this is just an introductory video on all of these concepts. We definitely will review these concepts in the next video, because we want to find relationships between work and different types of work, and yeah, different types of energy. So, to get energy for myself, I'm just going to eat some ramen while you all enjoy your studying. And ChemOly kids, you should stop watching this video. You should have stopped a while ago. Go do a practice test or something. Enjoy, have fun, and yeah, good luck everybody.